Welcome to qnawire.
So let's first write down the known quantities in the problem. So we have a point charge Q1 that is equal to negative 4 nanocoulomb, and this is placed on the x-axis at a distance 0.6 meter from the origin, and I'm calling that x1 so that it corresponds to the distance of Q1. And then we have another charge Q2 whose magnitude is unknown and we need to find that. And this Q2 is placed at a distance, let's say x2, that is given to be 1.2 meter, and this is also from the origin of the x-axis. And we need to find the sign and magnitude of Q2 for so that the net electric field is 50 Newton per coulomb in the positive x-axis. The net electric field at the origin due to both Q1 and Q2 is 50 Newton per coulomb towards the positive x-axis, and in the second case, the net electric field at the origin should be 50 Newton per coulomb, but in the negative x-axis. So in both the cases, the magnitude of the electric field is same, but the directions are different. So for the first case, let's find E1 and E2, that is the electric field due to each of these charges. So the net electric field at the origin, since E net is at the origin, so we need to find E1 and E2 at the origin only. So E1 will be equal to k times q1 over x1 square, because this is the distance from the origin, and substituting the values with k to be equal to, so k is the Coulomb constant, and this is equal to 9 times 10 to the power 9 Newton times meter square over Coulomb square. So now substituting the values over here, we get E1 to be 100 Newton per Coulomb. Now, similarly, we can find E2, and one thing we know for sure is the second charge, the electric field due to second charge must be in the negative x direction, because so that the second charge is negative and its magnitude has to be 50 Newton per coulomb. So E1, E2 is actually k times Q2 over R2 square. So one thing I forgot to mention is the direction of E1. So let's mark the vectors so that we can include the direction over here. So let me draw the axis so it will be easier for you guys to understand. So here is the point where we are finding the electric field, and Q1 is somewhere around here, Q2 is somewhere around here, and both of them are negative. Not both, Q1 is negative. So the electric field at P should be towards Q1 because Q1 is negative. So this is in the positive x direction. So this is actually I cap, has a direction I cap. And E2, let's say that Q2 is positive for now. So the electric field due to E2 will be in the negative x direction, because it will be away from Q2 since Q2 is positive. So negative x, and we don't know the value of E2 yet, but we do know the net electric field. So we know that the net electric field is actually 50 Newton per coulomb in the positive x-axis, so I cap. And by superposition principle, we say that the net electric field is actually the vector sum of E1 and E2. So this means that 50 Newton per Coulomb I cap is actually equal to 100 Newton per Coulomb I cap plus KQ2 over R2 square negative I cap. So this is for E2. Let me move on to the next page. So from here we can say that E2 vector, which is KQ2 over R2 square, R2 or X2. Okay, so this is actually, I have taken this to be X, not R. So let me just write X here. Yeah, so over here as well. The direction. So I'm basically solving this equation. So I'm taking this to the left side and bringing this value 50 Newton per Coulomb I cap to the right side. So this will give us 100 Newton per Coulomb I cap minus 50 Newton per Coulomb I cap. So this gives the net value to be 50 Newton per Coulomb I cap. So we know that KQ2 over X2 square negative I cap is equal to 50 Newton per Coulomb I cap. So now we can cancel out the directions, and that will give us negative K2 over X2 square. Remember, there is a negative sign here, so we need to include this and just cancel the positive part. So that is equal to 50 Newton per Coulomb. And from here we can find Q2, which will be equal to 50 Newton per Coulomb times square of X2 over negative K. And again, substituting the values because we already know them, we find Q2 to be equal to negative 8 times 10 to the power minus 9 Coulomb or negative 8 nanocoulomb. So we see that Q2 should have a negative sign in order for the net electric field to have this property. It should be 50 Newton per Coulomb and in the positive x-axis. And this makes sense because our E1 came out to be greater than the net electric field, which means that E2 has to be in the opposite direction so that the net magnitude is smaller than E1. Since E net is smaller than E1, therefore E2 has to be negative in order for that to satisfy. And this means that E2 has to be in the opposite direction or in the negative I cap direction, and this is only possible if Q2 is negative. So that's what we got, and so that's the first part. In the second part, the net electric field is in the negative x-axis. So the first two calculations stay the same because our charges are at fixed positions. We just need to know the magnitude. Only the sign and the magnitude of Q2 will change. So this is where the first part starts because E1 and E2 are the same. And again, let's consider the sign of Q2 to be positive so that the direction of E2 at point P is in the negative x direction and therefore negative I cap over here. So E net in the second part is in the negative x-axis. So this is 50 Newton per Coulomb negative I cap. And again, this is equal to E1 vector plus E2 vector. So we get E2 vector to be equal to E1 vector plus 15 Newton per Coulomb negative I cap, and oops, this is negative 15 Newton per Coulomb negative I cap. So this is E1 vector plus 15 Newton per Coulomb I cap. And E1 is similar to what we found over here, and that is 100 Newton per Coulomb I cap. So substituting that over here, we get this value to be 150 Newton per Coulomb I cap. And E2, let's substitute E2 as well. So E2 is KQ2 negative I cap over x2 square. So from here we find Q2. So again cancel the direction I cap and I cap because we just need the magnitude. And Q2 will be equal to 150 Newton per Coulomb x2 square over K. And solving this after plugging the values, we find Q2 to be 2.4 times negative 2O. Negative K, negative 2.4 times 10 to the power minus 8 Coulomb. Therefore, this can be written as negative 24 nanocoulomb. So we see that Q2 should again be negative for the net electric field to be in the negative x-axis, and the magnitude of Q2 should be higher than the magnitude of Q1, obviously because we need the net electric field to point in the direction of E2 now, to be opposite to E1. So E net is now opposite in the opposite direction to E1 and also has a lower magnitude. So which means that E2 has to be greater than E1 and E2 should also point in the negative x-axis. And that is only possible when Q2 is negative. Thank you.